Hello everyone. Today we are going to analyze a fixed beam when it carries a couple M in the center. In this analysis, we are going to find out the fixed end moments, reactions, and we are going to draw the shear force and bending moment diagrams. Also, we are going to find out the deflection and slope in the center and the maximum deflection and its location. To find out the fixed end moments, we are going to use Mohs theorems. First, let us use Mohs' first theorem. It states that the difference of slope between 2 points will be equal to area of moment upon EI diagram. Let us apply this theorem between the points A and B. The difference of slope between A and B is theta A minus theta B. In the point A, there is a fixed support. In the fixed support, there will be no slope. So, theta A will be 0. In the point B also, there is a fixed support. So, theta B also will be 0. 0 minus 0, we will get 0. So area upon EI is equal to 0. Now let us find the area of the moment diagram. We have to make the moment diagrams separately. In the point B, there is a fixed support. In this fixed support, we have the moment MB and the reaction RB. Let us assume that MB is acting in the anticlockwise direction and RB is acting in the upward direction. When we get the values of RB and MB, if we get positive values, our assumptions are correct. If we get negative value, that means our assumptions are incorrect. We are going to find out the moments in the point A from the point B. In this case, we are moving towards left hand side. Clockwise will be negative and anticlockwise will be positive. RB is acting towards the point A in the anticlockwise direction, so it will be positive, and the distance up to the point A is L, so RB into L. In the point B, the moment will be 0 because there is no distance, so we will get a triangular shaped diagram. MB is acting in the clockwise direction, so the moment will be negative. MB will not change, it will be constant for the whole length of the beam. In this case, we will get a rectangle shaped diagram. The couple or point moment M is acting in the clockwise direction, so the bending moment will be negative. This point moment also will not change. From the center to the point A, it will be constant. So here also we will get a rectangle shaped diagram. Let us keep this diagram as number 1, this diagram as number 2, and this diagram as number 3. Let us find area 1. This is a triangle. We know the formula for the area of a triangle: half into breadth into height. Here the height is RBL, the breadth is L. Using the formula, we are getting RBL square upon 2. Now let us find area 2. This is a rectangle. When we multiply MB with L, we will get the area. Since the diagram is negative, we have to apply a negative sign with the area. Now let us find area 3. This is also a rectangle. When we multiply m with L by 2, we will get the area. This diagram is also negative, so we have to apply a negative sign. We know that A upon EI is 0, but we have separated this area into three parts, area 1, area 2 and area 3. We can take EI outside and take it on the right side. EI into 0, we will get 0. Now let us apply the values of A1, A2 and A3. Let us take these two terms on the right side, so they will become positive. Here let us take LCM. We have to multiply MBL with 2. Then we can eliminate 2. From here we can take L outside. Then we can eliminate L and square. Finally, for RB, we are getting 2MB plus M upon L. Let us keep this equation as number 1. Now let us use Mohs second theorem. It states that vertical intercept of AB is equal to area of movement upon EA diagram into distance from A to centroid of movement upon EA diagram. The vertical intercept of AB is the tangent AB. Let us keep the area as A and the distance from the centroid as x bar. You can see that in the point A and in the point B there is no tangent because these are fixed supports. The elastic curve starts after some distance. You can see that on both of the sides. In this case, the tangent AB will be 0. Now let us find area into x bar. In the previous step, we have already found the area. So here only we have to find x bar. We are going to find out the centroid distance towards the point A. First, let us find x bar 1. This is a triangle. For this triangle, the centroid distance towards this height is 1 upon 3 into L. We will get L upon 3. Let us apply that. Now let us find x bar 2. This is a rectangle. For the rectangle, the centroid lies in the center. So we can easily find out the centroid distance. To find out the centroid distance, we have to divide the length by 2. So the centroid distance is L upon 2. Let us apply that. Now let us find x bar 3. This is also a rectangle, so we can easily find out the centroid distance. To find out the centroid distance, we have to divide the length by 2. For this rectangle, the length is L upon 2. When we divide L upon 2 by 2, we will get L upon 4. Let us apply that. Now let us multiply the area with the centroid distance. After that, we are getting these. We know that Ax bar upon EI is 0. But we have separated Ax bar as three different parts. Let us take EI outside and take it on the right side. EI into 0, we will get 0. Then let us apply these values. Let us take these two terms on the right side. They will become positive. Then let us take L square outside. Then let us eliminate this L square and cube. Then let us take this 6 on the right side. From the equation number 1, We know that RB is equal to 2mb plus m upon L. So instead of RB, let us apply this. Then we can eliminate L. Let us multiply these two terms with 6. When we do that, we will get these. 3 2s are 6, 3 2s are 6 and 4 2s are 8. Then let us take 3m upon 4 on the left side, so it will become negative, and 2mb on the right side, it also will become negative. 3mb minus 2mb, we will get mb. Here we can take LCM. We have to multiply m by 4. 4m minus 3m, we will get m. Finally, for mb, we are getting m upon 4. We are getting a positive value. That means our assumed direction is correct. In this equation, let us apply the value of mb. We can cut 2 and 4. Here it will be 2. Here we can take LCM. 2 into m, we will get 2m. m plus 2m, we will get 3m. Finally, for RB, we are getting 3 upon 2 into m upon L. We are getting a positive value. That means our assumed direction is correct. Now let us apply the rule sigma v is equal to 0 and find out RA. In this beam, there are two vertical forces, RA and RB. Both are acting upwards, so both are positive. We have already found RB. Let us apply that. For RA, we will get a negative value. That means our assumption is incorrect. We assumed that RA would be acting upwards, but our assumption is wrong. RA is actually acting downwards. Now we are going to find out MA. Let us assume that MA is acting in the anti-clockwise direction. To find out MA, I am going to take moment about A. In this case, I am moving towards left hand side. Clockwise will be negative, anti-clockwise will be positive. MB is acting in the clockwise direction, so it will be negative. RB is acting in the anti-clockwise direction towards the point A, so it will be positive, and the distance is L. The couple M is acting in the clockwise direction, so it will be negative. MA is acting in the anti-clockwise direction, so it will be positive. We can eliminate L. Then let us take these three terms on the right side. They will come with the change of signs. Then let us take LCM. Let us keep 4 as LCM. For MA, we will get a negative value. That means our assumption is incorrect. We assumed that MA is acting in the anti-clockwise direction, but our assumption is wrong. Actually, MA is acting in the clockwise direction. Finally, we have made the formulas for the fixed end moments MA and MB. Both MA and MB will be acting in the clockwise direction. Now we are going to draw the shear force diagram. Before drawing the diagram, let us find the shear force values. I am going to find the shear force values from the point A and towards the point B. In this case, I am moving towards right hand side. Upwards will be positive and downwards will be negative. RA is acting downwards, so it should be taken as negative. RB is acting upwards, so it should be taken as positive. Here you can see the shear force diagram. Now we are going to draw the bending moment diagram. Before that, let us find the bending moment values. I am going to find the values from the point A towards the point B. In this case, I am moving towards right hand side. Clockwise will be positive and anti-clockwise will be negative. Using the bending moment values, we can make the bending moment diagram. In this beam, in the point A and in the point B, there are fixed supports. In the fixed supports, there will be no slope. So theta A and theta B will be 0. Also, in the fixed support, there will be no deflection. So YA and YB will be 0. Now we are going to find out the slope and deflection in the center of the beam. We are going to use double integration method. Let us make a section XX at a distance of x from the point A. In this section, let us find the moment. We are going to find the moment from the point A. In this case, we are moving towards right hand side. Clockwise will be positive and anti-clockwise will be negative. MA is acting in the clockwise direction, so it will be positive. The reaction RA is acting in the anti-clockwise direction, so it will be negative, and the distance is x. Let us equate mxx with EI d square y upon dx square. Now let us integrate this equation on both the sides. When we integrate EI d square y upon dx square, we will get EI dy upon dx. For integrating these, we can use the integration formula. Using the formula, we are getting this. C1 is the constant. 2 into 2, we will get 4. Now let us integrate this equation again. When we integrate EI dy upon dx, we will get EIy. For integrating these, we can use the formula. After using the formula, we will get these. C2 is the new constant. 4 into 2, we will get 8. Then we can eliminate this 3 and this 3. In the fixed supports, there will be no slope. In the point A, there is a fixed support. So when x is 0, the slope dy upon dx is 0. In this equation, let us apply x is 0 and dy upon dx is 0. When we do that, we are getting C1, which is 0. In the fixed supports, there will be no deflection. So when x is 0, y will be 0. In this equation, let us apply C1 is 0, x is 0 and y is 0. When we do that, we are getting C2, which is also 0. In the EI dy upon dx equation, let us apply the value of C1. When we do that, we are getting this. This is the equation for the slope. Let us keep this equation as number 2. In the EIy equation, let us apply the values of C1 and C2. When we do that, we are getting this. This is the deflection equation. Let us keep this equation as number 3. Now let us find the deflection in the center of the beam, that is the point C. We know that this is the equation for the deflection. To find the deflection in the center, in this equation, instead of x, we have to apply L upon 2. L upon 2, the whole square, we will get L square upon 4. L upon 2, the whole cube, we will get L cube upon 8. Then let us eliminate L. Here it will be square. 8 into 4, 32. 4 into 8, 32. ml square upon 32 minus ml square upon 32, we will get 0. So the deflection in the point C is 0. Now let us find the slope in the center. For that, in the slope equation, we have to apply L upon 2 instead of x. We have made the section between the points A and C, so we have to name the slope as CA. L by 2 the whole square, we will get L square upon 4. Let us eliminate L and square. 4 into 4 we will get 16. Then let us add these two terms. When we do that, we are getting this. Then let us take this EI on the right side. It will come in the denominator. Finally, we have made the formula for the slope in the center theta CA, which is equal to minus ml upon 16 EI. Now let us find the maximum deflection. The maximum deflection occurs when the slope is 0. So we have to equate the slope equation to 0. Let us take mx upon 4 outside and take it on the right side. So we will get 0. Let us take this value on the other side. So it will become positive. Finally, we are getting x, which is equal to L upon 3. To find out the maximum deflection, in the deflection equation, let us apply L upon 3 instead of x. L upon 3 the whole square, we will get L square upon 9. L upon 3 the whole cube, we will get L cube upon 27. We can eliminate L. Here it will be square. 8 into 9 we will get 72. 4 into 27 we will get 108. Then let us add these two values. After adding, we are getting the maximum deflection. For the maximum deflection, we are getting a positive value. That means it occurs upwards. We have made the equations for the slope and deflection. These equations are only valid from the point A and up to the point C because we have made the section between these points. To make the slope and deflection equations from the point B and up to the point C, we have to make the section between B and C. But on the right side, no need to make the equations. In these equations, we have to just change the signs. This will become positive and this will become negative, and this will become negative and this will become positive. You can see that I have changed the signs. These two equations are applicable from the point B and up to the point C. So in this beam, there will be two places where the maximum deflection occurs. For AC, it will be upwards. It occurs at the distance of L upon 3 from A. For BC, the maximum deflection will be downwards. It occurs at a distance of L upon 3 from the point B. Similarly, in the point C, there will be two slope values. Theta CA will be above the span. Theta CB will be below the span. Now we are going to end this session. Thank you for watching this video.